Welcome to OptiMat Chat, an AI-powered agentic system that brings advanced materials discovery to your laptop. Unlike traditional tools that demand complex coding, OptiMat Chat uses a natural language interface, so you can run high-level atomistic simulations through simple conversation. It's a step towards Software 3.0, where human language becomes the code. Let's generate a material. Ask the agent to create a composition, such as a complex high-entropy alloy, and it uses universal machine learning potentials to build the model. Here you see a special quasi-random structure that captures random alloy behavior within a compact supercell. The agent also generates a radial distribution function plot, so you can quickly verify nearest neighbor distances in short-range order. Next, we request elastic properties of the generated material. The agent computes the elastic stiffness tensor and derives key mechanical properties, Young's modulus, bulk modulus, shear modulus, etc. The results are accessible directly in the chat, along with a heat map visualization of the elastic tensor. To move beyond 0K, we compute finite temperature behavior. Using the quasi-harmonic approximation, the agent evaluates the temperature and volume dependence of Helmholtz free energy, entropy, and isochoric heat capacity. From these, it derives temperature-dependent Gibbs free energy, the thermal expansion coefficient, and the bulk modulus. The results are presented as interactive, publication-quality visuals, such as 3D maps and 2D curves, so you can inspect finite temperature properties at a glance. Flexibility is built in. By default, OptiMat Chat uses OpenAI models, but you can switch in settings to a local, open-source small language model. That means zero-coding material science can run entirely on your own hardware, improving privacy and reducing dependence on GPU clusters or HPC. When calculations finish, the agent compiles everything into a single, structured summary in the chat. It begins with details of the generated structure, then moves to mechanical results, with a heat map of the elastic tensor and tables of computed properties. It also produces interactive 3D plots, such as Young's modulus and Poisson's ratio, where you can rotate, zoom, hover to inspect values, and download PNGs. Finally, it adds finite temperature results with both 2D curves and 3D surface plots, for example, isochoric heat capacity. At the end, you can export the full report as a PDF or download all raw data as a zip. Finally, every structure and property is saved into a living database. While conventional databases can't keep up with the vast design space of high-entropy alloys, ours grows with every conversation. You're not just using a tool, you're helping build an evolving map of the materials frontier.
The atomic structure suggests a novel material composition.
Fascinating. And its potential applications?